Okay, hey guys. So I keep getting questions on the separations homework, part A. So it's about how do you get a PXY diagram. So remember, right? Suppose you guys have a vessel, right? There's a liquid part and then there's a vapor part. So we know that there's a species 1 that can diffuse back and forth and a species 2 that can diffuse back and forth across some boundary. So how do we actually plot a PXY diagram? Well, a PXY diagram typically looks like this, where the top curve is usually the PX1 diagram for the ith species or A species in a binary mixture, and PYA is the bottom curve. The top line, right, is always going to be known as the bubble line. And then the bottom line is always going to be known as the dew line. So how do we get the first curve? So if we look at the first curve, right, clearly this is pressure as a function of XA. So let's do that using the modified Raoult's law and the Margol's equation with some assumptions. So the modified Raoult's law, to describe any binary mixture of anything, looks like this. Xi times gamma I, which is an activity coefficient, times the saturated vapor pressure of that pure species is equal to yi times p. Now again, just as a reminder, xi is the mole fraction of the ith species in the liquid phase, and yi is the mole fraction of the ith species in the vapor phase. So let's go ahead and expand this to write p as a function of xa. So we can expand this as follows. So xa times gamma a times PAV plus xb times gamma b times PBV is equal to YA plus YB, and we can factor out P, pressure, the total pressure of the vapor phase, like that. So key thing to recognize here is the sum of all these fractions is equal to 1. Likewise, we can do the same thing with this term, because the sum of all the liquid mole fractions is equal to 1. And we want just pressure as a function of XA. So we make the substitution using these known facts about all the fractions in this equation. They all must add up to 1 for both the liquid phase and the vapor phase. So let's go ahead and do that. So XA gamma A times PAV plus 1 minus XA times gamma B times PBV is equal to P. So we're pretty close. Now what we want to do at this point is take note that in the problem we're told that we can assume the following about the Margol's equation. So ln of gamma A is equal to lambda times xb squared, and ln of gamma B is equal to lambda times xa squared. Now gamma A and gamma B are activity coefficients. Also, this term lambda here is usually a function of temperature and is not the same for gamma A and gamma B. However, for the sake of the problem, we're told to assume that lambda is a constant. So we can do that actually. Why? Because in a Pxy diagram, each of these points that are plotted here are plotted at a constant temperature, where this system over here is allowed to reach equilibrium. And at equilibrium, the temperature is pretty much constant. So returning to this problem, let's go ahead and rewrite this all as a function of xa. So again, we can write lambda times 1 minus xa, because it's equal to xb squared, and then rewrite this as gamma a is equal to e, which I write as exp, to the lambda times 1 minus xa squared. Likewise, we can do the same thing with gamma b. Gamma b is exp, or e to the lambda xa squared. So let's go ahead and now plug these two guys in to this equation that we had before. So xa times e to the lambda times 1 minus xa squared times PAV plus 1 minus xa gamma b, hold on, sorry about that, is equal to times e to the lambda times xa squared times PBV is equal to P. And voila. Now we have over here pressure as a function of x1. So at this point, what we can do now is pick values for xa. We can pick values for xa and plot this and get half of the Pxy diagram as follows. So now I'll demonstrate this in Excel. Okay, hey guys, so here now we have a bunch of constants from the problem, so nothing special. So PAV is the vapor pressure pure species A, as if there is no species B present in the vapor phase. And likewise, same thing with PBV, which is the pure vapor pressure species B in the vapor phase, as if there is no species A present. So what do I do over here? From the function that I derived before, we can pick values for xa, as seen over here. So these are values we can choose. And then from here, we can designate constants that we have over there by putting a $sign before and after the letter of the cell in which the constant is located, as follows. For example, lambda is a constant, and we can see that it's in cell B3. So we put a $sign before and after the letter of the cell in which it is located to designate it as a constant. Once we do that, and we can go ahead and write out the rest of the equation as follows, with designated constants. Then we can copy and paste whatever in this cell all across the other cells with corresponding xa values. So let's evaluate the data and see if it even makes sense. So as xa approaches 0 over here, it makes sense that the pressure of the vapor will be about 20 kilopascals. So what does this mean? So as xa approaches 0, it means there is no species A present in our mixture. Instead, there's only species B. So that means xb should approach 1. So as xb approaches 1, the pressure of the vapor in our system will approach the pure vapor pressure of that pure species. So is this true if we look at the opposite end of the data? As xa approaches 1, it means only species A is present in the vapor phase. So it makes sense that pressure P of our vapor is 84 kilopascals, because if there is no species B present, then that means all we have is pure species A in our system, and thus the vapor pressure will be the pure vapor pressure of species A at 84 kilopascals. So let's go ahead now and plot this data and see if it makes any sense according to graphs we have already seen before. So here we go, right click, select data, add, and let's call this Pxa, or we can call this the bubble line. And let's pick our corresponding x values as follows. Right, and let's pick our corresponding pressures that are computed from our chosen values for Xa. And voila, what do you know? We got the Pxa diagram, or the bubble line. So we have half of the Pxy diagram. So let's go back and derive the Py diagram, or Pya curve, or the dew line. Okay, so now that you've seen in Excel how to get the Pxa curve, or the bubble line, now let's go ahead and try to get the dew line, or the Py diagram. So, to do that, let's start again with the modified Raoult's law. So, but we start with this. We know that P as a function of Xa looks like this. So, now let's go back to the modified Raoult's law. We know it's xi, gamma I, piv is equal to yi, p. So let's, instead of expanding it across all species in the mixture, let's just expand it across one species in the mixture and say that xa, gamma A, PAV is equal to YAP. So let's solve this for YA. So let's say YA is equal to XA gamma A PAV over P. Now we know what gamma A is because we solved for it previously. So we can say that XA times e to the lambda times 1 minus XA squared times PAV divided by P. But what is P? P is this. We can plug it here and write XA times EXP times lambda 1 minus XA squared PAV plus 1 minus XA times EXP times lambda XA squared times PBV. So what you have here is options here. You can either choose to take this whole term over here and say YA is a function of P, where you know what your P is from given values of XA, because you saw that in the Excel sheet where you have XA and you have P. From them, you can just plug in those P values as you did XA to get corresponding YA values. Or you can just write the whole thing XA directly as a function of YA. I mean YA directly as a function of XA, because you picked those XA values. And then the corresponding YA values should come, since this denominator over here is already equal to this p-value. So all of the equations can remain consistent this way. So it's your choice, however you want to plot it. So now let's go back to Excel and see how this looks. Okay, so here we are back in Excel. So here we have our YA values. You can see based on what was derived before, here we just have the same numerator that we saw before for YA, and then B6, or all those B values that we have in the denominator, are just the pressure of the vapor, or these pressures P that we have over here. So we can do that, or I could have taken this whole expression and put it in the denominator for YA over here, but why reinvent the wheel, right? So either ways, I get the appropriate YA values that correspond to this P value, which corresponds to the chosen XA values. So let's go ahead and plot these guys. So let's add the other series, call this PYA, or otherwise known as the do line, right? And then we pick our input series, which are these Y values. Then we pick our output values, which are these pressures. Okay, and voila, we have a Pxy diagram. So the Pxa is the bubble line, the Pya is the do line, because one's on top, the other one's on bottom. So this should all be sufficient for solving problem 2, part A of the separations homework. This should be pretty simple now. Yeah.